All right, so rational functions. All right, so we've looked at adding, subtracting, multiplying, dividing rational expressions. And so we're going to look at the functions then. And so all the rational functions basically work off the parent function 1 over x, which is this graph here. And with this graph here, you'll see that there are asymptotes. Who remembers what an asymptote is? Okay, Stephanie, what is it? Excellent, good. Okay, lines that the graph gets closer and closer to but never touches it. So the parent function 1 over x gets closer and closer to the x and y axis but never touches them. So we say that they have asymptotes at x equals 0, okay, which is a line, the vertical line x equals 0, or the horizontal line where y equals 0. And so what we're going to be doing is basically we're going to be taking those asymptotes and we're going to be moving them around. So we're going to be doing transformations with what we're doing. So here is, we're going to be looking at rational expressions in two different fashions. Okay, here's one right here. And in this fashion here, this takes that parent function 1 over x and basically just transforms it. The value of a tells us whether it's been stretched or compressed vertically. Okay, so if a is greater than 1, it's stretched out. If it's between 0 and 1, it's compressed. And if it's negative, then the graph is going to be flipped over. In other words, instead of it being in the first and third quadrants, it would be in the second and fourth. H is a horizontal translation, so a horizontal shift, either left or right. And then K tells us whether it's been moved up or down. Now, this is what I put on that little handout you've got. Okay? So you've got that little handout, and the top section of that handout is basically this information here. So we're going to do some transformations to start with. So K, once again, K is a vertical translation. So what K is going to do is take our horizontal asymptote, okay, the asymptote at the y equals 0, and then it's going to change it. So it's either going to move it up or move it down depending on whether K is positive or negative. And H is going to take our vertical asymptote at x equals 0 and is either going to move it left or right, okay, depending on whether H is positive or negative. If H is positive, we move it to the right. If it's negative, we move it to the left. Now, a reminder that if H is positive, it's still going to say minus a number. If it's negative, it's going to say plus a number, okay, because the formula says minus H. So the opposite thing happens there. So here we have the graph. We're going to use the graph 1 over x as our guide and describe the transformation and graph each function. So we have g of x equals 1 over x plus 2. So the thing we're always going to want to do is we're going to want to define what h and k are. So that should be the first thing that you write down is h equals this and k equals that. So Natasha, what's h in this case? Okay. All right, you're close. Okay, Nolan, you were shaking your head. What is it? You're shaking your head. Were you shaking your head no, that she was wrong? Oh, you weren't shaking your head? Okay, all right. Okay. Now, let's go back up here, Natasha, because this is an easy mistake that's made. Notice that this says minus h, okay? And this says plus 2. So it's negative 2, right? Exactly. All right, and that's the thing you have to be careful of, is that that's a very easy mistake to make, okay? All right, Mr. McCumber, what's k then? Where did you get 1? This number here? All right, let's look again. Where's k at? Okay, k is what's added on to it. Is there anything added on to it here? No, so what's k then? 0. Right? So this means that we have a horizontal translation 2 units to the left. Right? So here's our original function. Okay, 1 over x. This is the parent function here. Okay. So if we graph the translation 2 units to the left, then what's going to happen is then we're going to take all these points and we're going to move them over. So that new one's going to be then, let's see if I can do it. Oh, come on. Here we go. There we go. All right, so it's going to be shifted 2 units to the left. So where we had asymptotes at x equals 0 and y equals 0 is now going to be moved over here where x equals -2. But we didn't go vertically anywhere, so our vertical asymptote or our horizontal asymptote is going to stay the same. We'll talk about those more in a minute. Okay. All right, so all this did is move our graph over 2 units to the left. Letter B. Chase, what's the value of h? +3. Okay. So the one thing you can always remember is that the values of h are always going to be the opposite of what you think they are. Okay? Or the opposite of what you see. All right? I see -3, so h is actually +3. Okay? I see +2 here, so it's actually -2. All right, Brooke, what's the value of k then? 0. So once again, this is just going to be a shift 3 units, this case then, to the right. So if I draw in my graph, all right, so here's our parent function here. All right, so we're going to move our graph 3 units to the right. So that means I'm going to take this point here, which is at 1, 1, and move it over here 3 units to the right, which is going to put it there. And here I have a point at -1, -1, and that's going to be 3 units to the right. So 1, 2, 3, that's going to be here. So my graph then is going to look like this. Notice that I'm not crossing the x-axis, and I'm not crossing the line y equals 3. Okay? And so when you're actually going to draw these in, okay, you're actually going to draw dotted lines to represent those things. And we're going to identify those as asymptotes in just a second. But you have to draw them in. So when you graph them, I'm actually going to make a dotted line here at x equals 0, or y equals 0, excuse me. And then I'm also going to draw a dotted line here at x equals 3. Oops. Okay. Because my graph is not going to cross either of those 2 lines. Okay. The graph I draw in will not cross either of those 2 lines. And those are our asymptotes. And as Stephanie said, they get closer and closer to them, but will not actually touch them. Okay. All right, so I have a little note down here, okay, for accurate rational function graphs. All right. If you're graphing these on your calculator, all right, and you won't have as big of an issue on the 83 or on the 84s as if you had an 83, but I want you to go ahead and do this. I want you to graph letter B on your calculator. And I don't know if you'll have any problems with this or not, but we'll check it out and see. Now, does everybody remember how to put the fraction bar in your calculator? Okay, because it's a lot easier if you use the fraction bar. If you go to alpha, y equals, the very first one gives you the fraction bar. Okay. Now, I just want to make sure, did anybody's graph, is there a line down there through the middle? Or does yours look just like mine? What's that? The fraction bar? Alpha y equals. Oh, you don't have, okay, I have to update yours. All right, just go ahead and make sure you put your denominator in parentheses, so, but I'll update it for you today. All right, okay. All right, so does anybody's graph look like this one here? All right, so that was an old, what happened is that with some of the older calculators, with the TI-83 and like that, it would actually connect these lines, and so we had to make sure that doesn't happen. So as long as it doesn't happen, then we're good. Okay. All right, so let's look at, let's go back here for a second. All right, so I want you just for this, check it out here, I want you to identify H and K on both of these. Okay, so just identify H and K. Don't want you to graph them, just identify them. So on your sheet I gave you then, it basically has this information here. I forgot one thing that you're going to want to add. Okay? So this little part right here is on the top of that sheet. So for a rational function of the form f of x equals a over x minus h plus k, the graph is what's called a hyperbola. There's a vertical asymptote at the line x equals h. Okay? And this is the part I forgot. The domain is x cannot equal h. All right? So you're going to want to add on that same line there at the top. You're going to want to add domain x cannot equal h. And then it says there's a horizontal asymptote at y equals k, and the range y is not equal to k. So you're going to want to add those into there too. Okay? All right, so you're going to want to add the domain part and the range part in there on your sheet. Okay. Now, you're not going to be able to use this on a quiz, okay, or a test. All right? But I want you to have it because it's something then you'll be able to easily refer to, and then you can easily put whatever you feel like you need to on your note card. You can. You won't need all of it because once you do a few of these, then you'll have them down. Okay? All right, so we want to identify the asymptotes, the domain range of this function. All right, and then I'm going to show you again how the dotted lines come into our graph. So, and you can do this. When we're talking about vertical asymptotes, you can just use VA, horizontal asymptotes. You can use HA to represent them. Okay. Now, notice the thing is it says that it is the line x equals h and the line y equals k. So when you identify the vertical asymptote and the horizontal asymptote, you must say x equals and y equals. If you just put a number, it's wrong, okay? Because it's not a number, it's a line, right? So we need to identify h and k. So we have 1 over x plus 3 minus 2. So John, what's h in this case? Negative 3. So my vertical asymptote then is going to be that h, oops, not that color, h equals negative 3. And then that means that the domain is x cannot be negative 3. Abby, what's the value of k? Negative 2. So my horizontal asymptote is going to be that, and I just wrote that wrong. My apologies. This should have been x, not h. X equals negative 3. Sorry. So my horizontal asymptote k is negative 2, so I'm going to say y equals negative 2 for my horizontal asymptote. And I'll say the range then is that y cannot equal negative 2. Okay. Because what happens is the graph does not exist there because of the horizontal and the vertical asymptote. Right? So if I want to graph this then, the graphing of this is very simple since there's a 1 here. There's no in the numerator. So I'm going to draw in my vertical and horizontal asymptotes. Right? So that's the first thing I'll do. Is that it says I have vertical asymptote at x equals negative 3. So I go to negative 3, and I'm going to draw a vertical line there. Okay? And this is a line that goes on forever. And I go to y equals negative 2, and I draw a vertical line there, dotted line. Okay, it's not a solid line, it's a dotted line. Why would I put a dotted line? Okay, all right. So a solid line, it means it would actually be there. Okay, dotted line, it's not actually there. I'm just using it to divide my area up. Okay, all right. So my graph then is pretty simple for the most part. Right? So when I draw my graph in here, I'm going to have this point here and this point here. Now, because all I'm doing is I'm just taking this graph here, okay, and I'm just moving it 3 units to the left and 2 units down. And so the graph of y equals 1 over x has a point at 1, 1, and negative 1, negative 1. And so I'm just moving those points. So this graph is going to look like this. And make sure you put arrows there. Now, if that number in the numerator was different, okay, then you would have to adjust it according to that number, though, okay, just by multiplying. Okay. All right. Now, lots of times our rational functions are not written in that form. They're written as a polynomial divided by a polynomial. All those things we've been looking at as far as adding, subtracting, multiplying, dividing them, and simplifying them. And so more often than not, it's not going to look like in that form there. And so what we have to do is be able to take the form that we have and work with it. So these rational functions are called discontinuous functions because there's one or more breaks in the graph somewhere. Okay? A continuous function, though, doesn't have any breaks. So when you graph just a polynomial itself, it's not going to have any gaps or breaks in it, but these will. Okay? So here it shows us a graph of the quantity in the numerator is x minus 3 and x plus 2, and the denominator is x plus 1. Now, the things that we need to pay attention to with these are the fact that we have where the numerator is equal to 0 is where the graph crosses the x-axis. Okay? So when the numerator is equal to 0, the graph is equal to 0. So you can see that we have zeros at negative 2, 0 and at positive 3, 0. And then in the denominator, we have x plus 1. Well, what's the one thing we can't do when we divide? We can't divide by what number? 0. Okay? So if I put -1 in there for x, okay, then that would be undefined, wouldn't it? Because we can't divide by 0. And that's actually where we have our vertical asymptotes, is wherever the denominator is equal to 0. So even looking at these other ones here, the reason is because if we put h in for x, we would end up with 0 in the denominator. And so then it would be undefined. Okay? And that's why we have vertical asymptotes there. Okay? So here's and this is in the next part of that paper you have there. It says, if f of x equals p of x over q of x, that just means that we have a polynomial in the numerator and a different polynomial in the denominator. They have no common factors other than 1. Okay? All right, so we're not going to be able to cancel anything. We're going to talk about that when that situation happens tomorrow. Okay? So we have zeros at each real value where x of x for which the numerator equals 0. Okay, so this is when the numerator equals 0. And we have a vertical asymptote at each real value of x for which the denominator equals 0. Okay. So if the numerator equals 0, we have zeros. That's where it crosses the x-axis. Denominator equals 0, then we have vertical asymptotes. Right? And the graph doesn't exist there. Now, we're going to talk about this more specifically in a little bit tomorrow. Right? But this graph here isn't going to look like the last couple we've done. Okay? It's actually going to look like this graph up here. Right? And I'm going to explain why a little bit more tomorrow. And I'm going to tell you that each of these situations we have like this, the graph will look like that. But it's real easy to make the graphs. Okay, so they want us to identify the zeros and vertical asymptotes of this function. Now, just like we did when we were adding, subtracting, multiplying, dividing, the first thing we usually did was what? What, Colin? Factor. Okay, so the first thing we want to do is factor. So in this case, I can factor the numerator, but the denominator is just a linear anyways. So we have in the numerator x plus 4, x minus 1, and then over x plus 3. Okay. The reason we want to factor is because when I factor it, I can tell what the zeros are right away. Right? So Jessica, what are our zeros then? Right. Okay. -4 and 1 are our zeros. And I'm just going to put the numbers -4 and 1. Not going to say x equals, because when I start saying x equals, I'm talking about vertical asymptotes. Right? We're talking about lines. Right? So we're just going to put the numbers -4 and 1. Okay? Vertical asymptotes then. Chase, what's our vertical asymptote here? -3. Close to -3. What else do I need? X equals -3. Okay, all vertical asymptotes are x equals, horizontal asymptotes are y equals. Okay, so I also need x equals -3. All right, so if I'm going to graph this then, I'm going to start out and I have 0 at -4 and a 0 at 1. And it says I have a vertical asymptote at x equals -3, so I'm going to draw that in here. Now, there's one other point. There's only one other point I need to draw this graph, and you don't need your calculator for this, okay? Or you can use your calculator if you need to, but you don't need to. Okay? Can anybody tell me what the y-intercept is? What's the y-intercept? Okay, just think about it for a minute. And think about what does it take to make a y-intercept? What happens to get to y-intercept? All right. Cynthia, what's the y-intercept? Negative 4/3. How many of you saw that? Okay. Now, think about it. If I have the y-intercept, what's the value of x? On the y-axis, what's the value of x? 0, right? Okay. So that means I'm going to put a 0 here for the x squared, a 0 here for the 3x, and a 0 in the denominator where it says x. So if all those things are 0, all I have left in the numerator is negative 4. All I have left in the denominator is positive 3. So my vertical, or my y-intercept is at negative 4/3. Okay. Now, the reason this helps me is that it tells me then that this graph has got to go like this. All right, it tells me that. Okay, I know it doesn't tell you that yet. Okay, but you'll see that. And then it tells me then that down here, the graph is going to look like this. And one of the things that other sheet that I gave you, okay, when you get into pre-calculus, and which they're going to be talking about actually today, is that there is a line here that if we use long division, we could actually find what's called an oblique or slant asymptote. Okay, so there's actually a line here that those would get closer and closer to, but don't touch. Right? And in pre-calculus, if you take it, we'll talk about that. All right? So you can just graph this on your calculator, all right, and then just copy it on your paper then when you need to. Okay? But your zeros for the function are where the numerator is equal to 0. Your vertical asymptotes are where the denominator is equal to 0. And then tomorrow we're going to talk about, you'll see that on that sheet, there's two other things on your sheet. Something called holes and another look at horizontal asymptotes. And those are a little bit different, so we'll take a closer look at those tomorrow then. All right.